Hello, and welcome to our lesson on the different representations of 3D shapes and understanding cross-sections. In this lesson, we'll build on our existing knowledge of 3D shapes and apply it to new mathematical concepts. Here's the plan for today's lesson. We'll start by understanding how to represent 3D shapes using various methods like nets, isometric drawings, and orthographic projections. We'll explore what happens when we slice through a 3D shape and learn to identify and describe the resultant cross-sections. So far, we have built a strong foundation with the following content. Understanding different kinds of 3D shapes such as cubes, cylinders, and spheres. Calculating the area of 2D shapes like squares, rectangles, triangles, and circles. With this solid foundation, we are ready to delve into more advanced concepts. Understanding the different representations of 3D shapes helps us visualize and solve three-dimensional problems by simplifying them into familiar 2D views. Additionally, understanding cross-sections is critical in fields such as engineering and architecture. Let's get started understanding the different representations of 3D shapes. The first representation we'll look at is isometric drawings. Here's an isometric drawing of a cube. Does it look familiar? If you answered yes, then that's because isometric drawings are arguably the most common 3D representation used in everyday life. Isometric drawings provide a way to represent 3D shapes in 2 dimensions while maintaining a sense of depth. This illusion of depth is created by 120-degree angles between the X, Y, and Z planes. These drawings are typically made on isometric dot paper, which helps maintain the 120-degree angles. The next representation we'll explore is nets. A net is a 2-dimensional figure that can be folded to form a 3-dimensional shape. Let us take a cube, for example. We can unfold the cube to its net. The net is made of 6 squares arranged in a way that they can be folded up to reform the cube. To determine the surface area of a 3D shape, we can use its net. You can calculate the area of each individual 2D shape within the net and then sum them up. In the cube example, each square has an area of side length squared, so the total surface area of the cube would be 6 times the side length squared. We'll expand on this idea in future lessons. The third and last representation we'll examine is orthographic projections. Orthographic projections involve representing the 3D shape in several 2D views, typically from the front, top, and side. Let us take this 3D L shape, for example. We can construct its orthographic projection by examining it at multiple angles. Starting with the top, or plan view, it looks like an L. Moving on to the front view, we can see 2 rectangles. And finally, onto the side view, we can also see 2 rectangles. Note that their sizes are different compared to the front view. Orthographic projections preserve the ratios of dimensions. Those 3 views together give a comprehensive idea of the shape and allow us to understand the dimensions and relationships within it. We will now move on to cross-sections. Cross-sections are essentially the 2D shapes you get when you slice through a 3D object. Many 3D shapes, such as cubes, cuboids, and cylinders, have uniform cross-sections. A uniform cross-section means that the shape and size of the cross-section remain the same, regardless of where you slice the shape along a specific axis. For example, slicing a cylinder perpendicular to its base will always yield a circular cross-section, no matter where along the cylinder you slice. When asked to visualize a cross-section, imagine cutting through the shape and consider the 2D face that would be exposed. Going back to the cylinder, imagine we slice it parallel to the axis instead. Pause this video and have a think about what shape you will get. If you said a rectangle, then you are correct. Now imagine we have a cube that we slice horizontally. What would be the cross-section? Again, pause the video and try to visualize it. The cross-section in this case would be a square. A slightly harder example would be cutting the cube across one of its corners. Pause the video and have a think about the resulting shape. As you can see here, the cross-section would be a triangle. By mastering these techniques, you'll be better equipped to handle complex geometry problems, whether they involve calculating surface areas, interpreting technical drawings, or visualizing structural components. In today's lesson, we explored the different representations of 3D shapes and the concept of cross-sections. We began by understanding the various methods to represent 3D shapes, including nets, isometric drawings, and orthographic projections. We then delved into the concept of cross-sections, learning that they are the 2D shapes resulting from slicing through a 3D object and practicing identifying cross-sections by visualizing different cuts through various 3D shapes. Understanding these concepts is crucial in fields like engineering and architecture, where precise comprehension of 3D shapes is essential.